Right. Hello. For those who are listening, I'm David, and this is revision seminar for Maths 1M in 2016. Those of you listening from the future, hello from the past. And I'm going to start with some things on differential equations. Okay. Last week when someone asked me about that, I can't remember, one of you looks familiar but could be wrong, asked me about this. They specifically mentioned the part of solving differential equations involving the integrals themselves. So I will mostly focus on that, but I'll just, to orient myself, talk a little bit about differential equations. So a differential equation is an equation that's got a derivative in it. So, you know. Basically, with at least one derivative in it. There are many kinds of differential equations. If you go on and do more maths, you might even do a whole course called differential equations. If you do engineering maths 2A, you will do about 2/3 of that course is on differential equations of various kinds. They have ordinary differential equations and partial differential equations and second order and whatever, all sorts of different kinds of differential equations, and people have been studying them for almost as long as derivatives have been a thing. The key thing to note about a differential equation is that the goal is not to get a number answer. So with an ordinary equation where you have like x squared plus 2x minus 4 equals 7, your goal is to figure out which x's make that true. And so your goal is to find a number. But in a differential equation, the goal is to find a function. Find a formula for a function. That's the goal of a differential equation. It's very important to realize that. So when someone says solve a differential equation, your final answer will be y equals and there will be a formula at the end, or whatever. It might be not y, it could be t or p or whatever, but the final answer will be a formula. So for example, you might see something like that. The goal at the end is to get to y equals formula with x's in it. That's the goal of a differential equation. And it really is the most important thing that I could say about differential equations. When many people first meet them, they think the goal is to find a number answer, but that's not true. The goal is to find a formula. Unfortunately, there are times where you can't find a formula for x, and all you can do is estimate what y is at specific values of x, and that's what Euler's method is for giving up and not finding a formula for y, but just finding specific values of y that go with specific values of x. Okay, that's pretty much the deal. I could stop there if I wanted. You will, if you do Maths 1B in the future, learn more about different kinds of differential equations. In Maths 1M, you've only seen a couple of kinds. You've seen You've seen, you've seen a couple of kinds that you know how to solve, but you can always check if the solution to a differential equation is actually true for any kind of differential equation at all, whether you know how to solve it or not. So I'm going to start with that. Yeah. So checking solutions is the first thing you need to be able to do. And basically sub it in and see if it works, really. It's very important in an exam situation life, it's less important because you have plenty of time to waste in life. But in exam situations, you don't have time to waste. So it's very important to read carefully to tell if what they want you to do is find the solution and show all you're working for finding the solution, or just check if it really is a solution. And a good word to look for is check or verify. Verify means establish the truth of, in a literal sense. Verity means truth, and verify means truthify. And so your example might be something like verify. I'm just going to have to think for a bit and figure one out. Verify that y equals cos 3x is a solution of d squared y on dx squared equals minus 9y. Okay, so verify that y is cos 3x is a solution of d squared y on dx squared equals minus 9y. This is a differential equation. It's got a derivative in it. It's got a second derivative in it. So that officially makes it a second order differential equation. But at the moment, that's what it is. And you don't have to know how to solve a differential equation to check the answer. My answer says that the second derivative of y should be the same as minus 9 times y. So I'll figure out what both those things are and see if it really works out to be the same. So first I'm going to figure out what d squared y and dx squared is. Let's see. The derivative of cos is sine, but it's minus sine. Only because of this 3, I'll have to multiply by the derivative of the 3x, which will give me that. Okay? And the derivative of the minus 3 is multiplied on, so it will still be there afterwards. The derivative of sine is plus cos. And because of the chain rule, I have to times by the 3 again. And we'll get minus 9 cos 3x. Sweet. On the other hand, minus 9y is indeed minus 9 cos 3x. So this part here is the same as this part here. So d squared y on dx squared is in fact so it is a solution. Now that's not all the solutions to that equation. There are in fact infinitely many solutions to that equation. Sine of 3x will also do the trick. E to the 3x, e to the, no that won't. Maybe. Anyway, sine of 3x would also have done the trick, but that's not relevant to this question. The question is, explain to the reader why that really is a solution, and you can do that by just subbing it in. That's my first thing. So it's not really solving differential equations, it's just showing that you understand what the differential equation means. Okay, so that function is a solution because when I do the derivatives and sub it in, it gets the same answer. Sweet. I'm going to shorten differential equations to DEs. That's how mathematicians normally shorten that. So solving DEs, you've been shown two different kinds of differential equations that you know how to solve. There are a couple that you might be able to figure out along the way, but there's two that your lecturer expects you to be able to look at and just know. And the first doesn't really have a name. So I need to give it a name, but give me a second. Don't have a name for it, but it's all right. I'm just going to call them plain differential equations. And what I mean by that is ones that look like this, dy on dx or dy on dt or whatever is function of x. Okay? It doesn't have any y's in it other than in the dy on dx. It's just a plain old derivative equals. And you know how to solve them because the whole point of integrals is to undo derivatives. Solve the differential equation dy on dx equals 5x plus 7. Yay! This is not a particularly edifying one to solve, but it's one that you can do. Currently, the derivative of some function is 5x plus 7. I want to know what the original function is, and that's exactly what integration can do. Integration was originally developed to calculate areas, but it also happens to do a great job of undifferentiating stuff. So I can integrate. I can wrap an integral around the 5x plus 7 and it will create the answer. So the 5 is multiplied on, so it will still be there. X is an x to the power of 1, and so the power will go up and will divide by the new power. And the 7 will get an x attached to it. And the 0, which you can't see, will integrate to be a constant of some sort. But we don't know what that constant is at this time. So y is 5 on 2x squared plus 7x plus c. There you go. Lovely. I will stop and talk about integration in just a moment. Just as another example, give me a moment. Yep, that'll do. dp on dt squared is e to the 2t, for example. Just because it's a second derivative doesn't mean we can't do it. Again, there's no p's anywhere. Keep integrating until I make all the derivatives go away. So if I integrate once, it will turn a second derivative into a first derivative. And the integral of e to the 2t, well, if it was e to the t, the integral would be the same, because the integral of e to the t is just e to the t again. But it's not a 2t, it's not a plain t, it's a 2t. And the derivative of that's a constant, so I'm allowed to just divide by the derivative. That's the chain rule in reverse. And this trick will only work if the derivative is a constant. Only I need a plus c as well, because there's some constant that if I differentiated it, it would disappear, and so I need to put it in. And I'll integrate again. Now the p will be the integral of this. Let's see. Well, the half is a constant multiplied on and it will still be there. Oh, I should really put my integral sign in just to make it absolutely clear what I've done. So firstly, be really important that if there is something on the end there, the plus c, it has to be integrated as well. Everything has to be included in this integral. Let's see, a half is a constant multiplied on, so it will still be there. E to the 2t will go up to e to the 2t again, but I'll have to divide by that half, because that's how integration works. If I was differentiating, divide by that 2. If I was differentiating, I'd multiply by that 2, so since I'm integrating, I have to divide by it. And if that was a number like 7 or 2 or 5, an x would get attached to it. That would integrate to give that. And so it gets an x attached to it as well. And then we get another constant. Oh yes, because this isn't an x. This is a t. Good job. You know, I choose different letters deliberately to so that we get used to doing that, and then I don't do it right myself. So, well done. Just shows that it's an easy trap to fall into. And so I get that p is a quarter e to the 2t plus ct plus d. Now I don't know what either t or d, c or d are. That's what initial conditions are for. And perhaps the person who gives you this differential equation, or perhaps if you made it up yourself, you will know what the value of p is at certain values of t, and you can figure out what those letters are. So I might just do that, you know, what if we knew that p of 0 was 3 and p dashed of 0 was 2. What if we knew that? I'm putting 2 in because I've got 2 unknowns and I'm going to need 2 pieces of information to figure out what they were. Well, in that case, I know what p of 0 is. It's a quarter of e to the 2 times 0 plus c times 0 plus d. And this answer is supposed to come out to 3. So let's see, e to the 0 is 1, c times 0 is 0, and this is supposed to come out to 3. And so d is 3 minus a quarter, so 2 3/4, which would be 11 quarters. Is that right? 2 3/4, 2 would be 8 quarters. Yeah. So that tells me what the d is. And the c we still don't know, but my other piece of information involves a derivative, so I'll have to figure out what p dashed is first. Actually, I figured that out up here. dp on dt is here. I figured that out already. I have that answer here. It's a half of e to the 2t plus c. And so p dashed of 0 is a half of e to the 2 times 0 plus c, which is supposed to come out to the answer 2. And so c would be 1.5, which is 3 over 2. So actually, p is a quarter of e to the 2t plus 3 on 2t plus 11 on 4. So just going back to this equation here and putting in the values of c and d that I just found. Just there. Ta-da. All right, there you go. But again, the answer is still a function. Even though I've found what these numbers are, there's still t's here. Okay. So, are there any particular integrals that freak anyone out? That when they look at them, they go, don't know what to do? Yep.
Like sometimes when they involve sine
Sine and cos. All right. You know, interlude. Yep.
I always get mixed up between, like when you differentiate sine, so when you differentiate sine, it's cos, but if you differentiate cos, it's negative sine.
Mm-hmm.
Is there, like, so I was just wondering, why is it when you differentiate sine you get cos, and why is it when you differentiate cos you get negative sine?
Cool. I will cover that. So we're talking about integrals and therefore derivatives of sine and cos at this time. Let's do that now. Okay, integrals. Right, okay. Right. So when you do derivatives, it turns out that the derivative of sine is cos, and the derivative of cos is minus sine, but you can have a feel for why that's true. Tell me if this answer is unsatisfying. You can have a feel for why that's true by investigating what you think a derivative is. So, sine x looks roughly like this. I know sine goes through 0, 0, because sine of 0 is 0. I know that because sine is an odd function, and odd functions are rotationally symmetric around here. And that's just one of the information I need, I happen to know. And the derivative of sine, one way of interpreting the derivative is the slope of this graph at any given spot. So if I were, say, here, if this point here was, say, x, then this slope would be the derivative d on dx of sine x at that point x. Okay, that's what that slope would be. Because that's one way of interpreting derivatives. It's not the only way, but it's a good one. So let's follow what happens here. The slope at the very top here at pi on 2 is 0. And the slope at the very bottom here at 3 pi on 2 is 0. The slope here happens to be 1. So if you follow what the slope does as you move along, here at 0, the slope is 1. So I can draw a dot at height 1 to represent that slope. Here at pi on 2, the slope is 0. Here at this one, the slope is minus 1. And here at 3 pi on 2, the slope is 0 again. And I get this, which is what cos looks like. So one way of reminding yourself whether it's plus cos, whether when you differentiate sine, whether it's plus cos or minus cos, is to draw sine and go, what the slope at 0, is it plus 1 or minus 1? And it's positive slope here. And so it has to be positive cos. On the other hand, if y is cos x, which looks like this, here at 0, the slope is 0. So this is y dashed. And here at pi on 2, the slope is minus 1, so it goes down first. And so this one's going to go this way. And that picture is not sine, because sine goes up first. This is minus sine. So basically, because the slope starts being negative first, if you move forwards, the slope is negative first, which means your graph has to go down first, which means it's minus sine. That's one way of remembering it. I tend not to remember it that way, but I can at a pinch do that if I need to know that information. Integration is the opposite of differentiation, so everything's backwards with integration. I have this in my head. Integration is up and differentiation is down when I represent things. So my table of integrals for myself, while the one in the Maths Learning Centre goes right to left, left to right, in my head it goes up and down. So I have a list in my head that has sine x, and above it there's minus cos x, and below it there's cos x, because the integral is above and the derivative is below. That's how my mind works. I do that because when I do integrals of, say, x to the cubed, the powers go up, and so the integration is up. Okay, so in my head I have that cos x, sine x, when I differentiate it becomes plus cos x. Cos x, when I differentiate it, becomes minus sine x. Sine x, when I differentiate it, becomes minus cos x. Minus sine x becomes minus cos x, and then we end up back at the beginning again. Differentiation is down. So I only have to remember one of them, because if sine x differentiates to cos x, the other one has to be negative. So as long as I remember one of them, I can remember the other one. Whereas integration is up. So integration goes the other way. Cos x goes up to sine x goes up to minus cos x. That's the picture that's in my head. It's not an explanation at all, it's just a mnemonic, it's a way of remembering things. This is an explanation that has the graphs. And my final mnemonic, which is really bad, and many maths teachers would slap me. But if I'm going up the alphabet from C to S, then it'll be a plus. So, so sine to cos is down the alphabet, and if I go down, which is what differentiation is, it's the correct direction, so it's a plus. But sine to cos is down the alphabet, but I'm going up for integration, and so it will be minus, because it's the wrong way. If that doesn't make any sense to you, please ignore it. But that's just the way my mind works. Yes?
Do you know if in the exam, like during the reading time, are we allowed to write notes outside of the exam?
Yeah, so normally in exams you get given a piece of scribble paper, and you can ask for more if you run out of space. You're not allowed to write on the exam book itself, but you normally get a piece of paper, and you're allowed to write whatever you want on that piece of paper as soon as reading time starts. So when I did first year maths, I had this sort of mental cheat sheet. There were a couple of things that I had real trouble remembering, and I would repeat them to myself until I was able to write, and then I'd write them down. And that was my mental cheat sheet. And so you can't have too many of those things, because your brain can only hold about 7 things in memory. So don't leave too many of those things for your mental cheat sheet, but a couple of them. So I couldn't remember my my double angle formulas, and so for trig, and so I would repeat themselves myself and put them down. That's what I did in first year. Okay, there you go. So unfortunately, one of the best, you're going to have to remember some of these things. One of the best ways to remember things is to practice remembering them. So sit down with a blank piece of paper and go, what's the integral of cos, and write it down, and then check it. And then you'll go, ooh, I was right, or ooh, I was wrong. And that alone is enough to help you learn to remember things. Practice remembering. Looking at things and going, yes, that looks correct, is not good practice for remembering. You have to have a blank piece of paper and try to remember it from scratch. Okay, so there is a list of things that you need to just know, well, just know the integral and derivative of. And so in my head, this is my list of derivatives and integrals. So my differentiations and my integrals. So I know that cos goes up to sine and down to minus sine, where up is integration and down is differentiation. And sine goes down to cos and up to minus sine. I also know that tan goes down to sec x squared. And I don't know what the integral of tan is. I think it's like ln of sec x, but you're not expected to remember that. But that does mean that the integral of sec is tan, because any diff down arrow has an up arrow next to it that goes the other way. So, like that. So sec integrates to give sec squared, integrates to give tan, and tan differentiates to give sec squared. They're your trig ones. Your classics are that just any constant differentiates to give 0 and integrates to give cx. And any power of x differentiates. And I don't actually remember this as a formula. I can write it down as a formula, but what I remember is multiply by the current power and make the power 1 lower. Yep.
The integral of sine x, is it?
Oh, cos. Thank you. Thank you. One of the dangers of making up revision seminars as you go is you do that sort of thing. Which is why it's so important to check your answers in your exam. It would be nice if you could have someone check it for you, like just now. That would be awesome. But, yeah. But when you integrate x to the power of n, I'm going to give myself a bit more space. You do it backwards, right? When you differentiate, you multiply by the current power and the power goes down by 1. When you integrate, you put the power up by 1 first and then you divide by the new power. So I don't remember it as a formula, I remember it as that list of instructions. Integrating power up by 1, divide by new power, differentiating times by current power, power down by 1. And the only other ones, not ln, ln x, I don't know off the top of my head what the integral is. I can figure it out, but with methods that are in Maths 1A, when you differentiate ln x, you get 1 over x. Which means when you integrate 1 on x, you get ln x. Is that everything on your list? Oh, there's one more. E to the x integrates to give e to the x and differentiates to give e to the x. Doesn't matter which way round it is, but do remember, and it's worth putting it as a separate thing, that if it's got a number next to it, that e to the x, if you differentiate it, you'll multiply by the derivative. But if you integrate it, you'll divide by that derivative. Very important. That's just an example. And then finally, there is one more. If you just have any old number to the power of x, like that, if you integrate, well, if you differentiate it, that's not integration. If you differentiate it, it will be the same as what we started with, just like it was for e to the x, only you'll have to times by ln of a. And if you integrate it, it will be the same as what you started with, only you'll have to divide by ln of a. So when I remember these things, I remember some of them and then how to adjust the others. So I remember that the integral of e to the x is the same as what it was before, and the derivative is the same as what it was before. But if it's any other number to the x, then I'm going to have to adjust it by ln.
What if it's x squared?
X squared is in this category.
No, like e to the x squared.
E to the x squared you'll be able to differentiate but not integrate. So just let me do that example. E to the x squared, I can differentiate it. The chain rule says that, oh, that light is bad. There we go. The chain rule says it will be exactly the same as the derivative of just e to the x, but I'll have to multiply by the derivative of that, which is 2x. But it's not just question marks. The e to the x squared has no formula for its integral. There is no formula. No formula at all that can be written down. Can't be done. It totally has an area under its graph. It just, you can't write down a formula for it. That's impossible. Mathematically provably impossible. So if you saw an e to the x squared and you're expecting to integrate it, it would have to have a 2x or just an x next to it. So the final thing for integration is that if you happen to think of something that differentiates to give that answer, then that's the integral. And that's the way that they are wanting you to approach it. If you've done any maths in the past where you've done integration by substitution, you are allowed to use that method, but as far as I'm aware in Maths 1M, they're not expecting you to do formal substitution. They are only expecting you to notice something that looks like the derivative of something else. So the final one is that if you happen to have a function of another function, then when you differentiate it, you'll use the chain rule. And the derivative of the inside will come out. So if you happen to notice that what you have there that you're integrating happens to be the derivative of something and then a function of that thing, then you can integrate it, and it's best with an example. that one, for example, it looks freaky, okay? It doesn't fit any of my normal patterns. It's got two things multiplied together. That's 3x times sine of x squared plus 1. It looks freaky. But in any situation in which you were trying to do integrals, the first thing you would try and do is just rewrite it in a different format, which doesn't look like it's going to help. And then you would try doing substitution, which means what you'll do is you'll look at the insides of functions to see if the derivative of that is there. So I'll look at the inside of this sine, and the derivative of x squared plus 1 is 2x. So it's nearly there, it's 3x, so it's out by just a little bit. So you could just adjust it to make it a 2 if you wanted. Proper mathematician using dots. So I could just divide by 2 and times by 2 to make it into a 2. And then this happens to be the derivative of this. So, if I just had that and I differentiated it, well, not that, but cos really, and differentiated it, I would get, something with an x squared plus 1 inside it and a 2x on the outside. So what I can do is I can say, well, that's not there anymore. The 3 on 2 is still there because it's a constant multiplied on. If this had just been an x, the integral of sine x would be minus cos x. But it's not an x, it's an x squared plus 1, so the only way I'm going to be able to integrate it is if the derivative of that is there, which it is, so that's okay. So I'm going to get so that's 2x has vanished, and that's okay, because the only reason it was there is because when I differentiate this with the chain rule, a 2x will come out. You can do that if you want. If you really, really, really want to show a lot more working than that, you can just check that that works. Let's just differentiate it and see what we get. So the 3 on 2 is multiplied on, so it'll still be there. The minus is multiplied on, so it will still be there. The cos will differentiate to give minus sine. And because of the chain rule, I'll have to multiply by the derivative of that, which is 2x. Which is, the minus minus will cancel, the 2, that's a times sign here, by the way. That 2 will cancel with that 2, and I'll get 3x sine x squared plus 1. It does in fact work. The derivative of this is what we started with, and so therefore the integral will be the other way around. So this is my check. You can always check an integral by differentiating it. I should probably have put the 3 on 2 next to the cos. It's better to have a minus 3 on 2. That looks simpler, but that's the idea of sort of using the chain rule in reverse. If you are familiar with the process of integration by substitution, it would probably be easier to do that without having to think forward and backwards simultaneously. If you wanted to do this by substitution, you could say u is equal to x squared plus 1 and see what happens if you're used to doing substitution. And that would be acceptable in your exam, by the way. But that's not part of your course, so I'm not going to do it right now. Okay. Right. I think that's it. That's pretty much everything. I could do any number of examples, and feel free to come to the Maths Learning Centre and talk to me and my staff about doing that. But one of the key things is to try and find things you're familiar with. So you've got two things to look for now. You have functions that you're familiar with, and you just know their integrals and derivatives, and things being inside other functions and their derivatives being on the outside. I'm just going to do a couple, maybe one more. Let me integrate that. A lot of people don't get this right the first time, and it's partly because it's got multiple different things happening at once, and so they focus on one of them and not the other. That's normal, especially in a stressful situation. So what I wanted to do was show it to you. If this was an x on the bottom, it would be 1 over x, and the integral of 1 over x is ln x. Well, technically absolute values. Technically absolute values. It's not an x, but the derivative of what is there is a constant. So I can just pretend it's an x and divide by that constant derivative. It's a classic trick, and you're allowed to always do that trick. Any time where you would know what to do if it was an x, but instead of an x it's something that has a constant derivative, well, you can just do it as if it was an x and divide by that constant derivative. Derivative of this is 2, I divide by the 2. I can do it with e to the power ofs as well. I'd know what to do if that was just an x, the integral would just be e to the x. But it's not an x, it's a 5x plus 7, and the derivative of that is a constant, so it's okay to just do this. If the derivative of that wasn't a constant, I'd be stuffed. And the only way to deal with it would be if whatever the derivative was here, multiplied on. So if it was 5x squared plus 7, no hope. But if instead, if I had like an x 5x squared plus 7, x e to the 5x squared plus 7, I've got a chance, because that x is nearly the derivative of the top. All right, that's my little integral interlude, unless someone has more questions about integrals, which I'm happy for. Yep?
What happens when you have like a linear term to the power of 4 or something?
Something like that?
Yeah.
Just got to make sure my pages don't get lost. All right. Okay. This is one of those same situations. If that was just an x, I would know what to do. It would be x to the power of 4. And so it would be power up by 1 and divide by the new power. That's what I would do if it was just an x. It's not an x, and the derivative of what is there is a constant, and so I can just divide by that constant. And then a big plus c at the end. So, idea is, I look and say, well, there's something inside something else. The thing on the inside, its derivative is a constant, so I can just pretend that it's just x, and then divide by the constant derivative. You okay with that?
Yeah,
it takes some focus, and you get used to focusing on those things to say, ah, well, it would be, only it's not, and so I'll adjust it like this. That's basically the idea. Yep?
Does that work if that was like 1 over?
Yep. It's great to have what-if questions like that. Okay, if it was just 1 over stuff, I'd use ln, but that only works if it's 1 over x, not 1 over x to the 4. So I just need to be a bit more creative first. If that was 1 over x to the 4, ln wouldn't work, because I'd need the derivative of the x to the 4 to be there already. But 1 over x to the 4 is the same as to the minus 4. And now I can do the same thing I would normally do. The thing in there, its derivative is a constant, so I'll just have to divide by that along the way. The integral of something to the minus 4 is to the minus 3 because we go up by 1. 1 up from minus 4 is minus 3, and I'll divide by that new power. But it's not an x, it's a 12t minus 3, so I'll have to divide by that derivative. Actually, it's very good to ask yourself those sorts of what would happen if questions, or at the very least ask a teacher what would happen if questions. Anytime you've gotten to the end of any problem, especially while studying for exams, it's a great thing to say, all right, what would have happened if it was this? What would have happened if it was this? What would have happened if it was this? And if you can answer all those questions, then you'll be good for your exam. Because no exam question's ever going to happen again, not quite the same anyway. Feeling good? Sweet. All I would say is just be really careful with those minuses when you do integrals of things like sine, because they just tend to disappear. Even if you put them in first time, you'll forget them the second time, so just focus. Possibly put them in a different colour. That can help. Okay, back to the thing. So where just a second, where have we been? We've had differential equations. We've had the plain kind, where its derivative equals something and there's no... that p, the variable that names the function, is only there once. What if the variable there that names the function is there more than once? In Maths 1M, you're only taught how to deal with one kind of that function. One kind of differential equation of that kind, and it's called separable. Separable DEs. Okay. So, right. So separable DEs are a kind of differential equation that is allowed to have more than both variables, the y and the x, or the p and the t, or whatever the variables are allowed to appear more than once. But it's a very special kind. It's possible to separate them from each other by only using multiplication and division. So I'm going to write that down in words. It's possible to separate the y's and the x's, or the p's and the t's, or whatever the variables are, only using times and divide. Okay? I'll show you what that means in a second. Okay. So in your notes it's written in a certain way, but I find that unhelpful, so it's just easier to do it as an example. So my example is that dy and dx is, say, like that, for example. The key of what you're looking for is that it looks like, or can be rewritten as, something involving only x times something involving only y. That's what I've got there. So if you rearrange it to get dy and dx equals, then if you have a piece involving only x and another piece involving only y, you can do it. Where involving only x might mean there's no x's there at all. So I'll just do a couple of them. So what I mean by separating it, it's possible to separate this to have all the x's on one side with the dx. No, yeah, from your perspective it's this one. And all the y's on the other side with the dy. And we're going to treat the dy over dx as if it's a fraction that can be split apart, because it works. And when integration and differentiation were first invented, that's how Newton and Leibniz did it. Okay, they treated them as if they were individual entities, the dy and the dx. Today, we get all funny about limits and stuff, but you know, when we're doing this sort of thing, we're allowed to do it because it works. Okay, so using only multiplication and division, I'm not allowed to add or subtract anything. I need to turn this into something. Y is attached to the dy and x is attached to a dx. So I'm going to multiply by dx, like that. And then I'm going to remove this y squared by dividing by it. Sweet. So now I've separated the x and the y's. The y's are all over as part of this expression here, and the x's are all part of this expression here, and they're not connected to each other because they're on opposite sides of the equal sign. And now I can just integrate both sides. Like that. When you see it written down, it doesn't look like there's two steps there, but the first step is to separate them, and then the next step is to whack the integral signs in. Okay. Well, let's see. 1 over y squared, well, if it was 1 over y, I'd use ln, but then the derivative of y squared would have to be there, so that's not going to work. So it would be really best if I just rewrote that as a single power. Excellent. So, y to the minus 2, the power will go up by 1, and I'll have to divide by the new power. This x is currently x to the 1, so the power will go up by 1, and I'll have to divide by the new power. And I'm going to need a plus c. I don't need the plus c on both sides, because if I put a plus c on one side and a plus c on the other side, they're actually different c's from each other, so it's like a c1 and a c2, and I can just subtract one of them and combine them together, and I'll get another c. So I only need to put it on one side. And currently I'm not finished. Yes?
Can I just ask, does it matter which side you put the C on?
No, it does not matter which side you put the c on, but it works better if you put it on the x side. Because your goal is to get y equals. That's the goal. You know, whatever the top function is, whatever this top variable is, there, the goal is to get that equals something. So if you put it on the y side, you'll only have to subtract it later, and it's just a waste of time. So put it on the x side. All right, but worthy point, my goal is to get y equals. It's not finished yet. So I'm going to have to deal with all of this. So first I'll do what I normally do when solving equations. Powers have to be dealt with last, because I would do them first. So I'll get rid of the minus. Technically minus c. If you want, you can replace that with a new constant. I like to change my letter to remind myself that I did that. So all of the numbers at c could be, some of them are negative, some of them are positive. If I do minus c, well, that's all the same numbers, but in a different order. And so I could just replace it with a new constant. And then this y to the minus 1 is 1 over y. In fact, I might just go back and change that. And so I will have to do 1 over both sides to figure out what y is. It is vitally important that you treat these things, including the constant, as a single number, so that when you do any operation on them, the plus d is included in it, or the plus c or whatever. So this thing here, I did 1 over this and it got me y, and I did 1 over this blob here and it produced this. Do not just do it over this bit. The plus d has to be included in it, or it's wrong and it doesn't actually satisfy the equation anymore. And now there is my final solution. Ta-da. Not particularly pretty, but there it is. That's separable DEs. And there are a couple of key moments that happened there. The first thing that happened was I separated the x's and the y's. The second thing was I integrated. And then the third thing was I rearranged it to get y equals. And I was very careful about including this plus d in here. I want to do something that has a little nuance in it, just to point out that separable DEs may not look separable to begin with. Let's do it with some different letters. Random thing. That doesn't currently look separable, but it is, because I can rewrite it so that it has a piece with t's and a piece with p's. They've both got a t in them, so I can bring it out. Like that. And now, it will be possible to separate the t's and the p's simply by doing multiplication and division. So I'll times both sides by the dt, and I'll divide both sides by the 2 plus p. Like that. And now the p's and the t's are separated from each other, and so I can just whack my integral signs in. So now I've got two separate integrals to do. If this was just a 1 over p, I'd use ln. But it's not a 1 over p, it's a 2 plus p. But the derivative of that's a constant, so I can just pretend it's a p. So it'll be ln. But I'll have to divide by the derivative, but the derivative is 1 anyway, so it's okay. And t will go up by 1, and I'll divide by the new power. Sweet.
Can I just ask?
Yep.
If you were to try and put that then in times of t, and so first thing you do is you take e for both sides,
Mm-hmm.
and then in that you would need to include c in what you put to
I'm just about to do that.
Okay.
So that's good. So I'm going to have to get p equals, and my friend over there has preempted it, which is great. And tell me if I don't say the thing that you want me to say, okay? So I'm going to need to get the p all by itself. The furthest thing from the p here is the ln. I'll have to deal with that first. Which means I'll need to do e to the power of everything. So e to the power of this will give me that, and e to the power of this will give me this.
Then would you change the c to a different letter?
I would like to change the c to a different letter, but it's not going to do anything at the moment because it's trapped up inside this e. But I can deal with it because what I'm going to do is I'm going to say, well, e to the power of things with a plus up in the power becomes times down below. So I can write that as that. This plus c up here, e to the power of, and things with a plus becomes a times down below. Nearly there. Now you're just going to deal with this absolute value sign. Traditionally you're supposed to put it in there. It could be a plus or a minus, depending on whether the 2 plus p is positive or negative. Nearly there. Now I can replace the c, well actually all the stuff involving the c that's not attached to anything else. This thing here, all of that, is a constant. I don't know what it is. E to the c is some constant, e to the c is some other constant, plus of it and minus of it are other constants. I can replace all of that with a new constant. Traditionally they call it a. Like that. All of this bit here has become this a here. And finally I will subtract 2 from both sides. And I'll get that. Yay! Now it really is done because I've got p equals. If I was told that p was a certain answer at a certain t, then I could figure out what that a is. And I wouldn't need to figure out what this c is back here, I could just figure out what that is there. So for example, if p of 0 was, say, 5, then I'd get that when I sub in 0. Half of 0 squared is 0. And that would be 5. A minus 2 would be 5, which means a would be 7. And so therefore P is 7e to the half of t squared minus 2. So I don't have to figure out what the C is, because I can just figure out what the A is instead.
If you got the plus minus e to the c from doing a square root instead,
Yep.
could you still do the same thing and get rid of the plus minus or both?
Only if it could be separated out from the other things. So you're asking if I had something like that.
All squared,
Sorry?
all squared,
Like there's an all squared here,
none both sides.
right?
That plus the square root.
All of that.
Yeah. Maybe. And take square root of all that.
Like that.
Yeah.
Yep, you could combine that together into a constant.
Okay.
What I was saying is that sometimes you'll get something like something like that. Not that, sorry. That. What if that? And then you'll get that. Because the plus c is trapped inside the square root, I can't join it with the plus or minus, so I'm just going to have to leave it like that, and it's either plus or minus, and I'm going to have to decide later which one it is based on whether p is positive or negative. So that's sad. And that's the sort of thing where if I'd had that and I had something like p of 0 equals 10, say, then I would have said, well, p of 0 is minus 2 plus or minus root c. And the only way this could possibly be 10 is if it's the plus. Because if it was the minus, I would have to be subtracting it. So can only be true if plus, and so therefore we've got minus 2 plus root c equals 10, and from there I can figure out what c is. I don't know what sorts of things they're going to give you and how many nuances they'll have, but I would say this is all useful thinking if you have to do dynamics next semester, if you're, say, doing an engineering degree, because differential equations come up in dynamics, which is one of the reasons they're in Maths 1M. Or, like, you know, Physics 2, you know, 1B. All right, that's probably quite enough of that differential equations, unless someone has other questions about it before I move on, because I might as well put them in the video, and that's okay. All right. The only other thing I could mention is Euler's method, but I do have some examples of that on the video that's already there, so I might leave it at that and try and cover some of the other things people asked about.